Good evening. We'll start the ninth live session for this payment materials course. And this today's discussion would be including the assignment 8 questions discussion from the past week, and also we will discuss the summary of week 9 lectures, and we would solve few questions in relation with the week 9 lectures. So as far as last assignment questions are concerned, the first question is asked that an open graded bituminous mixture is produced using Marshall compaction, and the dry weight of the sample in air is given as 1256 grams, and also the weight of the wax is given as 40 grams, and this wax weight is used to coat the 1256 grams of the dry weight. So the weight of the coated sample in the water is 650 grams. So they have asked us to calculate the bulk density of the bituminous mixture if the specific gravity of wax is given. So this is a direct question. So we know the formula as mentioned here. Dry weight is given as 1256, and the paraffin coated mass in air is usually, they haven't given it directly, but that can be calculated as dry weight of the bituminous mixture is 1256 plus weight of the wax is 40 grams. So this would be 1296. So except that remaining all have been given directly. This is the dry mass in the air, which is 1256. Specific gravity is given, and the wax coated mass in water is given as 650. This is 0.85, and this is again 1256. So paraffin coated mass again is 1296. So if we substitute these values, we will get the specific gravity as 2.097. And if we come to the second question, calculate the volume of effective bitumen using the following data. So GSB is given. GSB is nothing but the bulk specific gravity of aggregates are given, and also the bulk specific gravity of mixture is given, specific gravity of bitumen is given, percentage of bitumen 4.5%, and the GMM at that 4.5% is given as 2.510. So they are asking about volume of effective bitumen. So when we say volume of effective bitumen, if we know the total bitumen content or OBC, from that if we deduct the absorbed bitumen, so whatever is remained is actually volume of effective bitumen. So this total bitumen content is already given as 4.5%. Then we need to calculate the absorbed bitumen. So to calculate the absorbed bitumen, we need the details which they have given. For example, if you see the bitumen absorption, we need the effective specific gravity, we need the bulk specific gravity of aggregates, we need the specific gravity of bitumen. This is directly given, this one also given. So we do not know the effective specific gravity of aggregates. So how do we calculate? This is the formula for calculating the effective specific gravity, where all other details have been given. So if we calculate the effective specific gravity, and by substituting here, we will get the bitumen absorption. Once if we get the bitumen absorption, we already know the total bitumen is 4.5%. So total bitumen is, let us say, 4.5%, and bitumen absorption after calculating, let us say you got 0.8%. So if we remove this, you will get whatever is effective bitumen, and we need to observe that this effective bitumen is percentage by weight of total mix. But in the question they have asked calculate the volume of effective bitumen. So you need to calculate the volume from this. This is by percentage by weight of the mix. How do we calculate the volume when we have the weight? Because we already know the specific gravity is given. If we know the specific gravity, from the specific gravity equal to the weight by volume, and if we already know the weight, volume can be calculated. And if we see the third question, a bituminous mixture is prepared whose weight in air is 1265 grams and the SSD weight is given and the weight in water is given. GMM was measured to be 2.515. Calculate the percentage solids. So when I say percentage of solids, if your total mixture is, let us say, 100%, if we remember the phase diagram, which consists of aggregates, bitumen and the air voids, in this total mixture 100%, if we remove the percentage of air voids, whatever remain will be percentage of solids. So how to calculate this percentage of air voids? To calculate the percentage of air voids, GMM minus GMB by GMM will give percentage of air voids. So GMM is already given in the question, which is 2.515, but they have not given GMB. So how to calculate the GMB? We know GMB equal to weight in air divided by SSD weight minus weight in water. So they have given the weight in air, they also have given SSD weight and they have given the weight in water. So if we substitute, we will get the GMB value. Once the GMB you got, you can substitute and get air voids as 7.87%. So the final question answer what they have asked is percentage of solids. Once you get the air voids, 100 minus that percentage air voids would be your percentage of solids. And these are very simple theoretical questions. Bitumen content chosen on the right side of the minimum VMA. In VMA, binder content graph will lead to. So if you could have recalled that graph which we have for VMA, VMA versus binder content. So it was always suggested that whenever our optimum bitumen content it satisfied the specification of VMA minimum, we need to make sure that our OBC is not on wet side. If it is on wet side, there is a higher bitumen content than the required, which will lead to the bleeding in the mixture. The criteria of set for VFB. So if we again recall the voids filled with bitumen, this VFB usually calculated from the data of VMA and the air voids. So if we already have the criteria for VMA and also air voids, why do we even need to check for the VFB? Let us say if you take the VFB, they have mentioned the limit of 65% to 75%. That means there was a minimum limit and also maximum limit. The purpose of mentioning this is, let us say if VMA is this much volume, if I don't specify the minimum voids filled with bitumen, there is a chance of having lesser bitumen content than the required. And if I don't specify this higher limit, there is a chance that bitumen content can exceed the whatever is required. So in order to limit the minimum and also the maximum bitumen content, there is a purpose of this range of minimum to maximum. And this also will help us, but that option is not available here. So in addition to this, it also helps us to maintain the maximum limit for the VMA, because in the codal specification only the VMA minimum is specified. They have not mentioned what is the maximum limit for VMA. By limiting the voids filled with bitumen, we can actually indirectly limit the maximum VMA also. So if we see the options, option A says it helps in limiting the maximum VMA value. We can see the curve here. So we always prefer VMA minimum on dry side. So in superpave mix design, deleterious material is. So if we could have recall superpave mix design, before performing the superpave mix design, the aggregates have been subjected to two types of properties. One is consensus properties, another is source properties. These are like mandatory properties that needs to be satisfied, like fine aggregate angularity, coarse aggregate angularity. But when it comes to the source properties, which are not mandatory but it is suggested to be satisfied, this deleterious materials, which is like sand equivalent test which we perform according to the IS specifications. So we see the amount of clay percent present in our fine aggregate. So this deleterious materials is actually comes under this source property. And this question, which was elaborately discussed in the video. So during the assessment of design aggregate gradation, the following assumption is considered. So whenever there was an increase of 1% in the air void, how much will be the increase in the VMA percentage? This has been in detail discussed with one example in the previous live session also. It would be 0.1 to 0.2%. And this is again a simple question where the bitumen is 63 grams and the aggregates are 1200. So if the bitumen is 63 grams, how much will be the OBC or binder content on this total mix? So aggregates are 1200 grams plus bitumen is 63. So total mix will be 1263. So this bitumen in this total 1263 in terms of percentage would be. This is what the question is. And this is 4.99%, that means around 5%. In a bituminous mix with 4.5 binder content, calculate the value of GMM if the effective specific gravity of aggregate is 2.767 and the specific gravity of bitumen is 1.02. This is also again a direct question. Bitumen content is given and effective specific gravity is given and the specific gravity of bitumen is also given. So if you see the formula, everything is given. You need to calculate the GMM value in this. So this is given, this is given, this is given. GMM needs to be calculated. If the VMA of a bituminous mixture having a binder content of 4.8% is calculated to be 14.2. So VMA is given as 14.2 and the binder content is 4.8. What should be the bulk density of the mix? Assume that bulk specific gravity of aggregates is 2.671. This is also a direct question. So where VMA is already given, they are asking for GMB. What should be the bulk density of the mix? And the GSB is given as 2.671 and PB is given, VMA is given. So if we come to the recent week lectures, this week 9 summary includes the Marshall mix design. Briefly, it has been discussed in regard to the standard and modified Marshall mix design, and also the superpave mix design has been discussed. Then the detailed hot mix recycled asphalt mix design and the cold mixes have been discussed. Let us go to the summary in very brief in half an hour or so. So we already know how to design the Marshall mix design given the aggregates and binder content. Mostly this Marshall mix design is based upon impact compaction and we subject this mix to various blows. It can be 75 blows, 50 blows or 35 blows depending upon the traffic level. If the traffic level is greater than 1 MSC, we always consider 75 blows. And if we are doing for the gap graded mixes where the expected air voids is not the 4%, it will be more air voids in the gap graded mixes, then the blows would be around 50. So the hammer weight and also fall has been given. This is for the aggregates whose nominal maximum aggregate NMAS is less than 25 mm. If we take dBm, let us say dBm 2, let us consider its NMAS is 26.5 if we specifically say. So for those mixes whose NMAS is more than 25 mm, we need to actually go for modified Marshall mix design. The only difference would be in the standard Marshall mix design, the specimen size would be 100 by let us say 101.5 63.5, let us say. The specimen sizes would be different and also the hammer weight would be different and also the stability flow conditions would be different. So when we consider the standard Marshall mix design, once the specimens are prepared, these specimens would be conditioned for around 30 to 40 minutes in the water bath at 60 degrees. Otherwise, if water bath is not available, for 2 hours to more than that in the oven. Then those samples will be tested for stability and flow value, and the loading rate would be around 51 mm per minute. So most of the times it happens that we could not able to produce the mixes with 63.5 mm height. In those cases, the correction for these height are being provided. So the height should be corrected. Thereby the corresponding stability value will be corrected. As far as the flow value is concerned, if we take the MORTH specification limits, it has been provided, let us say 2 to 5 mm as the flow limit range. For unmodified binders, it is always achievable, but if we take the modified binders like polymer modified binders, so due to their higher elasticity, there is a chance that those mixes can be subjected, those mixes can produce higher flow. So their flow can be more than 5 or anything. So in those cases, just based upon the maximum flow value, we cannot say that these modified bitumen mixtures are having higher flow. So they would be lesser in the performance. We cannot say. So this upper limit for the flow values, especially for polymer modified bitumen, should be weighed off. So in the cases where NMAS is more than 25, as we were discussing previously, if we wanted to perform the modified Marshall mix design, so those specimens should be tested for stability and flow again, but the stability of those specimens would be around 2.25 times than the standard, and also flow value should be around 1.5 times than the standard. So these are the details. Hammer should be, previously it was around 4.5 kg, it was double mostly, and the diameter is not 101, here it is 152, and the height also not 63.5, it is 95.2, and the sample required in the Marshall standard Marshall would be around 1200 grams of aggregates plus around 50 to 60 grams of binder, so it should be around 1250, but here it is 4 kgs in here. And the number of blows, as far as, let us say in standard, if you consider 75 blows for traffic greater than 1 MSA, here you have to take 1.5 into 75 blows as the blows. The main difference between this Marshall mix design and the Super Pave mix design is the kind of compaction to which we are subjecting the mix to, because in Marshall the compaction is always the impact, whereas in Super Pave mix design, if you remember, the mix would be subjected to a near field condition where the load of around 600 kilopascals of vertical pressure would be applied with an angle of 1.16 degrees, and it will be applied in multiple gyrations. It is kind of rotations. So this number of gyrations depends upon the purpose for which we are actually preparing the mixes. Let us say depending upon the traffic level, if the traffic is less than 30 MSA, the expected traffic if it is more than 30 MSA, if it is in between 10 to 30 MSA. So based upon the requirement to which we are actually designing the mix for, so the N initial, N design and N maximum. So there are 3 criteria. Our mixes which we are designing in the lab, they should satisfy these criteria. For example, if I design for greater than 30 MSA, it might be mentioned that, let us say, N initial should be X. Let me say X number of gyrations. So let us say X is 10 gyrations. So when I use 10 number of gyrations on this mix, it should provide particular air voids. Then we can consider that mix as a appropriate mix. So there are 3 conditions. Let me discuss in detail here. So if you see N initial, N design, and there is another criteria called N maximum. What is this N initial? So initially we choose certain amount of aggregates, and also we choose the corresponding OBC or binder content. Then we prepare a mix. This mix would be subjected to the continuous gyrations. Let us say now I am interested in an initial. So if you see here, there is a table. If I am designing for less than 0.3 million standard axis, my N initial will be 6 gyrations. So whatever the aggregate plus bitumen I have mixed, that mixture, the standard condition of 600 kilopascals of vertical pressure, 1.16 degrees of angle will be subjected to these 6 gyrations. So what is our final criteria? After this mix is subjected to the 6 gyrations, we need to check that whatever the final mix that has been produced, the specimen, that should have around 11% to 9.5% of air voids. So that is what mentioned here. If you see here N initial, so it should have 89 to 91 point, uh, 89 to 91.5% of GMM. Okay. When I say GMM is 89, that means GMM represents the percentage of solids. If the solids are 89, out of 100, if I remove this 89, whatever remaining, that means 11 will be the air voids. And if you see here, around 9.5 will be the air voids. Why do we need to check this initial condition is, so when here we are actually checking the compactability of the mixture. What if I could not able to achieve the air voids as 11%? If my air voids are more than 11%, that means otherwise if my air voids are less than 11%, that means my mix is getting compacted too much than the required. So corresponding to the 6 gyrations which I have selected for whatever the traffic condition, if it is not providing this 11% air voids, either it is providing lesser or more, that means too much of air voids will lead to the durability issues, lesser air voids will lead to the rutting resistance. So this is the initial criteria. This is not the final criteria. So any mix should satisfy this 89 to 91.5% of GMM. So once that is satisfied, what if it is not satisfying? What do we change? I have chosen a particular aggregates binder content. I have prepared. Then I have seen that my air voids are not within 89 to 91.5. That means my air voids are less than 89% or more than 91.5. Then what we have to do is we need to change this weight of mix. So we change the aggregate and weight of mix, and again we mix in such a way that at the end again we will check for the 89 to 91.5% of GMM corresponding to the N initial. So at the end, after doing all the trials, we will get a particular amount of mix weight. Initially, let us say I have tried with 2.5 kg. Then I got particular air voids. Then I will change this weight. Then let us say next time I will take 2.6 kg and I will add corresponding OBC and I will check for the air voids. If this is giving the criteria required, that is 89 to 91.5% of GMM, then I will finalize that weight. So every time you need to use that amount of weight, so that because that weight and the corresponding binder is satisfying the initial criteria. Once that is done, the same weight we need to check for N design. So why does this N design is for? So N initial is to check the condition whether our mix is being able to compact properly or is it compacting too much or not. So once if I wanted to design, what is the main criteria in our Marshall mix design also? 4% of air voids. So this 4% of air voids, when I say, that implies 96% of GMM. So 96% of GMM implies that after laying the pavement, if you wait for particular number of years, let us say 5-6 years, the initial whatever mix I have placed in the field will get compacted. Then we expect that pavement would be having 4% of air voids. So at end design, let us say previously we have selected less than 0.3 MSA and initially 6. Now what is the end design specified for that particular traffic? It is 50. So for the same aggregate and bitumen mix, we use 50 gyrations and we try to compact then we will calculate the air weights. How do we calculate these air weights? The specimen we will calculate the GMB and we will calculate the GMM. GMM minus GMB by GMM will give the air weights. If those air weights are 4%, that means our mix is satisfying the 96% of GMM. So once these two are satisfied, that is not the final mix, because we also have to check for another, that is N maximum. Let us say in the field, if the vehicle traffic is too much, that is more than the expected, then we have to limit our mix air voids in the mix to the least possible. Let us say 2%. According to the specification of N maximum, our air voids in the mix should not be less than 2%. Because if the air voids are too less, what happens? Especially in the summer, there is no sufficient air voids to expand the bitumen. In summer, bitumen will try to expand. There is no space. Then what happens? All the bitumen will try to ooze out. It will come out. That will cause one of the problem as bleeding. And another thing is, when I say that the air voids are less than 2%, that implies that there is a more bitumen in the VME, voids in the mineral aggregates. Whenever there is a more bitumen, which implies that there is a rutting problem. So that will result in the plastic mix. So all the mixes in the superpave gyratory compaction should satisfy this N initial, N design and N maximum criteria. So the amount of aggregate and binder, that means which is nothing but the asphalt mixture, the weight which satisfies, the weight and the combination which satisfies this N initial, N design and N maximum, that would be taken for further either performance tests or the mix designs. So you don't need to remember this. Let us say these are the specimen sizes. You can observe that the specimen sizes are different from the Marshall design. So 150 is the diameter and height would be 115. And nowadays we also have the molds to prepare this 100 mm diameter. And the diameter is chosen in such a way that the diameter should be 4 times of nominal maximum aggregate size. This is to avoid the end effects during the compaction. So, if you remember in the Marshall mix design, once the volumetrics are satisfied, we actually perform the stability and flow test. Those are kind of strength related tests. But in the superpave mix design, there is no mandatory criteria that this mix, whatever has satisfied N initial, N design and N max, should satisfy a particular strength test. There is no criteria. So, there is no specific strength test. Yet, it is always recommended that we have to perform the moisture test and other performance related tests to ensure the volumetrics are satisfying all the field related performance. So the 4% corresponding to the end design is what the optimum binder content, and at that binder content we expect that all the other volumetrics like air voids, voids in mineral aggregates, voids filled with bitumen and fines to the dust ratio and also GMM at the initial, all these should be satisfied, and there are certain specification tables has been given. So after determining and finalizing the OBC, the moisture sensitivity and N maximum criteria is checked by preparing the samples. So this extra tensile strength ratio test, so which is actually to understand the moisture sensitivity or also the stripping nature of the aggregate from the bitumen. So this is in brief about the Marshall and also superpave mix design. So let us move to the reclaimed asphalt pavements, which is nothing but the RAP. So when we already have a constructed pavement and we have been observing that those pavements will be failed after a particular number of years. So once after they have failed, let us say we wanted to collect that material and we wanted to reuse that material in construction of the other pavements or at the same pavement. So this RAP is actually aggregates that are coated with the bitumen. So when I collect the already existing pavements, those aggregates are not just aggregates. Those aggregates have, so let us say this red color is aggregate, there is some coated bitumen. That is the reason why all the tests that we are going to perform on this wrap are not direct. Let us say specific gravity of aggregates. How we perform on virgin aggregates is completely different from the wrap aggregates. Because in the virgin aggregates, aggregate is the only single specimen. But here aggregate has some bitumen coated over that. So how do we actually go forward with this wrap related test? So when every time if somebody says, let us say my asphalt mixture is 100%. That means you have 100 kgs of asphalt mixture. So in this 100 kgs of asphalt mixture, I wanted to use, let us say, 50 kgs of already used pavement. That means wrap as 50% wrap, and remaining 50% I wanted to use virgin aggregates. So when I say wrap percentage as 50%, so this 50% is not the aggregates percentage. We need to represent the wrap percentage in terms of binder. That means, let us say if I have 50 kgs of wrap aggregate. So we will take these aggregates. All these aggregates have some amount of binder coated over that. So we need to determine how much amount of binder is present in this 50 kgs. Let us say of this 50 kgs, 10 kgs is bitumen. So 10 kgs by 50 kgs into 100. Let us say 50 into 2. So total 20 kgs. That means in this total 50 kgs of wrap, 20 kgs is binder. So total mix is 100%. In that 100%, 20 kgs of binder will be around 20%. So now the wrap percentage will be 20%, not the 50%. So wrap percentage will always be represented in terms of amount of binder in the wrap, because that is what actually going to involve in the mixing or blending process. So you have to remember this. This has been already specified also. So it's better to represent percentage of wrap by percentage of wrap binder. Okay. So for example, there was an example also which we can discuss again. Let us say 20 percentage of wrap. As we have already discussed, there is a 20 percentage of wrap. So when we see directly 20 percentage of wrap, what do we think? So wrap percentage is 20. So out of total 100 kgs of mix, 20 kgs is wrap and remaining 80 is new aggregates. Then we cannot directly say 20 percentage of wrap. So now we have to find out what is the binder content in this wrap. So in the question they have given that 7% is the wrap binder. So out of this 20%, 7% is the binder. 7% is the binder. So and it also has been given that the total mix has 5% of binder. So let us say 7% is the binder in this wrap. So to this wrap I am going to add two new binder, new aggregate, then I am going to prepare the mixture. Okay. So then after preparing the mixture, my final OBC is 5%. So in this total 5% of OBC, the 7% of binder is coming from the wrap. So if we calculate this value, let us say you will get 28%. So we have to represent the wrap percentage as this, which is nothing but the 28%. So let us say if I decided the amount of wrap percentage, how do I even proceed? So irrespective of the wrap percentage, let us say you can use the wrap percentage more than 25, less than 25 or in between also. So irrespective of whatever is the percentage of wrap, initially there are few things that needs to be calculated. Let us say one is the binder content. So when we get the wrap amount, initially we have to calculate how much is the binder content in that wrap. So to calculate that binder content, we have two different methods. One is the ignition oven, where we need to heat these wrap aggregates at higher temperatures. So there is a chance that at higher temperatures these aggregates may cause degradation. So it is not suggested to use this ignition oven. And there is another method which is called as solvent extraction method. So in this method, we use the RAP aggregates and we mix with the solvent and we try to separate the amount of binder from the RAP aggregate surface. So using these two methods, initially we have to calculate the binder content. Once that is done, so whatever the aggregates remain, so those aggregates are not are of same size. So they might be having different sizes. So we need to calculate we have to perform the sieve analysis. That means in the given amount of aggregate, what are the percentage of each size of aggregates. So we will be doing that gradation. So these are the two basic mandatory things that needs to be performed irrespective of the RAP percentage that we are going to use. So now coming to the specific cases, let us say my RAP percentage is around more than 25%. So whenever the RAP percentage is more than 25%, so in order to design those RAP mixes, you need to go for some charts called as blending charts. So those blending charts actually require the physical properties of the RAP binder. So we will discuss about that in the upcoming slides. So in order to give that input of physical properties, whenever the RAP percentage is more than 25%, we need to perform the physical properties of RAP binder. What are those physical properties? We will discuss in upcoming slides. So once the binder is, let us say we have performed the physical properties. So on the RAP aggregate surface, I have removed the binder now. So whatever the aggregates I have, what should I do now? I need to calculate the specific gravity of those aggregates. It is exactly like the virgin aggregates. So how to calculate the specific gravity? When I say specific gravity, that is bulk specific gravity of the aggregates. But this bulk specific gravity process might not be same because this still might have some bitumen surface. So how to go about that? So in those cases, there are three methods that have been mentioned to calculate the bulk specific gravity. So the main method is if the RAP percentage is lesser than 20%. So whenever the RAP percentage is less than 20%, we calculate GSC, effective specific gravity. So to calculate the effective specific gravity, what are the requirements? We need to know the PB, which is the amount of binder content. So that we will actually already we got from here. So initially when we got the RAP, we already calculated the amount of binder content. So we already have the PB. And we also need GMM, theoretical specific gravity. Let us say somehow we have calculated the GMM. So if we know the PB and GMM, and we can calculate the GSC. So if our RAP amount in the total mix is less than 20%, we can directly take this effective specific gravity as the bulk specific gravity. So it doesn't affect the volumetric that much. But whenever the RAP percent is more than the 20%, it was observed that the volumetric, especially the VMA, is changing variable, varying too much. That is the reason why whenever the RAP percent is more than 20%, do not directly use this effective specific gravity as the bulk specific gravity. So what do we need to do in those cases is, let us calculate the GSC till that step, that is fine. Using that GSC, if you see the formula here, which is bulk specific gravity, if you know the GSC, you can substitute here. But what is unknown here? Binder absorption. This binder absorption is what we have to assume based upon the water absorption of the aggregates. So once if we assume the binder absorption, by substituting the binder absorption and effective specific gravity, we can calculate the GSP. So we can use this GSP as the bulk specific gravity of the RAP. So in the previous cases, when we are calculating the GSC, we have seen that we need the value of GMM. But the calculation of GMM is not direct here, because in the virgin aggregates, we usually coat the virgin aggregates and then we use those coated loose aggregates to calculate the theoretical specific gravity. But when we take the RAP aggregates, when they have come from the field, what happens? There was a process in the plant where there was a chance that RAP aggregates might be crushed at some sides. That means some of the sides of the RAP aggregates might have stripped bitumen. So bitumen might not be there at few surfaces. Then what happens when there is no bitumen? When we keep these loose aggregates in the water to calculate the theoretical specific gravity, there is a chance that these aggregates may absorb the water, which will change the value of theoretical specific gravity. So before proceeding for the theoretical specific gravity, we need to make sure that all the wrap aggregates are coated properly with the bitumen. So how do we do that? Initially, when we have the wrap aggregates, we keep them in the oven for around at a temperature of 110 degrees, and to these heated wrap aggregates we add the bitumen of 1 to 3% by the weight of the aggregates. So we assume that adding this 1 to 3% by weight, it will completely coat the wrap aggregates. Then once after coating, then you can dry them, and again the process is completely same. We use the pycnometer. We fill the loose aggregate binder coated loose aggregates into this pycnometer, and we proceed with the process, and this is the formula to calculate GMM. So once the GMM is calculated, we know one of the process is directly substituting GMM here and calculating the GSC, and we will take this GSC as we will consider the GSC as the GSB, and we will proceed. Again, if the RAP percentage is more than 20%, then we'll again come to this formula and calculate the GSP. So this is the process of calculating bulk specific gravity and theoretical specific gravity. So I have mentioned previously that there was a need to calculate the binder physical properties when the RAP percentage is more than 25. So what are those physical properties? Let us say if my wrap mix design is based upon viscosity grading, then that physical property is viscosity at 60 degrees using that Cannon-Manning viscometer. If my wrap mix design is based upon the PG, then we need to calculate the critical temperatures. When I say critical temperature, the exact temperature at which the superpave specification, let us say G star by sin delta for rutting, and also G star into sin delta for cracking. So it should be actually 2.2 kilopascals if we test the RTFO samples, and it should be 5000 pascals, so kilopascals. So these are the specifications that needs to be met. So at what temperature wrap binder can able to take this minimum criteria, that temperature is what actually called as critical temperature. So these are the two separate properties required based upon the kind of grading system we are going to use to perform the wrap mix design. And another thing that needs to be remembered is, if the wrap percentage is less than 15%, let us say I have a wrap aggregates and I have extracted the bitumen on this wrap, and whatever I have extracted, that bitumen I have tested viscosity, and from the viscosity I have found that the viscosity grade of that bitumen is VG30. So now the wrap would be a kind of stiff material. We know that. So once the wrap material is stiff, we need to add some softer bitumen so that in order to improve the fatigue resistance. But if the wrap percentage is less than 15%, it is suggested that you can use the same VG30 kind of binder. But if the wrap percentage is 15 to 25%, use one grade lower. That means, let us say if wrap has VG40 binder, then you can use one grade lower means VG30. Okay. If the wrap percentage is more than 25%, we cannot directly choose the grade of the binder. We need to use the blending charts to determine the grade of the binder. So let us see what is that blending chart. And two other points that needs to be remembered is, in these blending charts, it is assumed that, let us say there is a aggregate, and above this aggregate there is already some amount of binder that is being coated. To this I am going to add a new binder, because already existing binder over the wrap surface is very stiff. So I need to add some soft binder so that the mixing and also the compaction would be easier, and also it will improve the performance of fatigue. So when I added this new binder, we know this new binder is, let us say, VG30. This coated binder is VG40. We are here assuming that this VG40 and VG30 are going to blend completely. That means when I mix this VG40 and VG30, we are not sure whether they will blend perfectly or not, but we are assuming according to this blending chart that they will blend 100%. This is one of the assumptions that may not be true. And in no case the virgin binder grade be more than 2 grades softer than the desired. Let us say if the wrap binder grade is VG40, this should not be less than VG. Let us say if I choose VG10, that means that is 2 grades lesser. It should not be lesser than that VG10. So then what happens if it is less than 2 grades softer? Then that softer binder will be dominating the wrap binder. Thereby there will be a problem of rutting again. So if we look at the blending charts, so this blending chart, if you see, on y-axis it is viscosity and on x-axis this is new binder. So in this blending chart, there are two possibilities of asking the questions. The first probability is, if you see the x-axis, it starts from 0, 10, 20, 30, 40, 50, 60, 70. And above 0, there is something called 100. That means that 100 implies 100% of wrap, that grading. When you see 0, that means virgin aggregate 0, new binder 0. Then again 10 means 10% of new aggregate, 20, 30, 40, 50. When you go to the last, it will be 100%. Okay. Initially, when I say 100%, 100 just above the 0, that implies that is 100% of wrap. Let us solve few questions, then we will understand this. So here there is a possibility that determine the appropriate binder grade if the wrap percentage is fixed. Let us say wrap percentage is fixed. This 70 is aggregate percentage. Here the wrap is 30%. So they have given 30% is wrap and target grade is fixed. And that what is the target grade, that is also fixed. So they may ask what is this wrap binder viscosity. Okay, this is the target this is a new binder viscosity. They might have given this, they may ask this. In some cases they may give this wrap binder viscosity and they may give this target viscosity. They may ask you for new binder viscosity. So there is only three possibilities, 1, 2, 3. And this is 4, wrap percentage. They can give wrap binder viscosity, wrap percentage, target viscosity. They may ask new binder viscosity. Out of four options, they might give remaining 3 and will ask us to calculate other. So when we solve a problem in the upcoming slides, we will clearly understand this. Okay. And in addition to this wrap, another concept that has been discussed is cold bituminous mixes. So as we have discussed in the previous lectures, the warm mixes. So hot mixes, we actually heat the bitumen more than 150 degrees. That is exact corresponding to the mixing temperature, let us say. Even we heat the aggregates at the higher temperature so that we expect that bitumen and aggregate mixture will be compacted properly. So in order to achieve the same compaction but at lesser temperatures, we have been progressed to warm mix asphalts. So whose temperature would be around less than 150. That would be around 40 degrees lesser approximately. And again in half warm mix, again a little bit lesser than the temperature. And when it comes to the cold mix asphalts, where the temperatures are extremely lesser than the other three methods. So the main advantage is especially the sustainability, where we do not want to use higher energy consumption to heat the aggregates or binders, but still we wanted to have the better workability. So if you could see here the summary, where the cold mixes usually compact mixed around 0 to 30 degrees range. Half warm mix asphalt in 60 to 100 degrees. Warm mix asphalt 100 to 150 degrees. But hot mix asphalt, as we already know, they will be heated more than 150 degrees. So currently we are discussing about this cold mix asphalt, where the mixing temperature would be, or production temperature is in the range of 0 to 30 degrees. What is this cold mix asphalt usually? So this cold mix asphalt is, let us say, previously we used to have virgin aggregates plus binder. We were applying some heat from outside, let us say greater than 150 degrees, then they both will get heated, then we try to mix. So then what are we usually doing when we apply the heat? We are trying to reduce the viscosity of the binder so that it will go and coat all the virgin aggregates. So without heating, also if I could able to reduce the viscosity of the binder, then we can eliminate the heat and we can also serve the purpose of coating the aggregates. That is what the purpose of emulsion, which we have already discussed. So we have used the bitumen some percentage, and we have used some emulsifier, and also we have used the water, and we have blended them in one equipment, and we have tried to reduce the viscosity of the bitumen. Then this emulsion would be coating the aggregates completely. So that is one of the process. In addition to this, let us say if I wanted to use lesser temperatures further, then what we do? We use this cold mix technology, where we take the emulsion also part of this cold mix technology, and then we take the aggregates. So we know already in the emulsion there is a particular amount of water that is available. So in addition to that, we have another amount, extra amount of water to lubricate the aggregates and to improve the workability. So initially when the aggregates are there, to that amount of aggregates, we add more water to improve the lubrication. In addition to that, we already have emulsion, which in default has the water. So using these three, emulsion, aggregates and additional water, is what we call this cold mix preparation materials. These components, in addition to these components, we also can add further, that is to improve the strength of the mixes. So that comes an additional. So if we don't want to improve the strength, we don't need to add anything extra. If we wanted to improve the strength, it is suggested to use cement, fly ash, lime or other supplementary additives. So this cold mix, so how do I design? How do I know that how much emulsion I have to take, how much extra water I have to take, and how much water in the emulsion I have to take, how much aggregate gradation and what is the type of aggregate gradation, how do I choose in such a way that at the end I need to produce a bituminous mixture that can produce with a better performance or better stability. So let us briefly see the steps involved in the design of cold asphalt mixtures. The first step would be calculation of initial residual bitumen content and initial emulsion content. So we know that emulsion is the part of this cold asphalt mixtures. So when I say emulsion, this emulsion already has bitumen, water and some emulsifier. Let us keep this water and emulsifier aside. So emulsion has bitumen. So first step is we have to calculate. So whenever I am using this emulsion, that means whatever the bitumen present in the emulsion, that is what will be available to coat the aggregates. So first we have to understand how much bitumen is present in this emulsion. So the calculation of initial residual bitumen content is nothing but the calculation of amount of bitumen present in the emulsion. So once if you know that, you can calculate the initial emulsion content. So how do we calculate that initial residual bitumen content? We know that this amount of bitumen in the emulsion depends upon the amount of coarse aggregates, fine aggregates and fillers. If the fillers and fine aggregates are more, we know that the amount of bitumen present would be more. So we have an empirical formula presented here, 0.05 into A, where A represents the coarse aggregate percentage, 0.1 into B represents the fine aggregate percentage and C represents the filler percentage. If we substitute the percentage of coarse, fine and filler, we can calculate the initial residual bitumen content. So we know that initial residual bitumen content would be some X percentage of emulsion. Let me erase this. So some X percentage of emulsion. Okay. But from the empirical formula, now I know this value, initial residual bitumen content. Once if you know this initial residual bitumen content, if we want to calculate the emulsion, we can calculate, right? Emulsion would be initial residual bitumen content divided by the X percent. Okay. So this is how we actually calculate the initial emulsion content. So our main aim is to find out how much emulsion we have to use. So this emulsion is actually the initial residual binder content if you know. So that X is the bitumen content percent in the emulsion. So if you know the initial residual bitumen content, from that we can calculate the initial emulsion content. So once if I know the emulsion and also the bitumen content, next step would be keep that bitumen away. So what is the next part in the emulsion? Water. So I also have discussed that in addition to the water present in the emulsion, we add another extra water, that is to provide the coating or pre-wetting of the aggregates or whatever the aggregate percentage that we are going to, or gradation we are going to use. That water we call as pre-wetting water. So initially we have to choose certain amount of water and we have to confirm that that water is sufficient to completely wet the aggregates. So this is the water content at which mix is neither too sloppy nor too stiff. So if I add some particular water content, mix should not be very slurry like mud and it should not be very stiff. Okay. So how do I confirm that it is not too sloppy or not too stiff? So there are two tests. So let us say I take some random amount of water content. I will add with these aggregates. Then I will observe the coating. So if the coating minimum 50 percentage of material is coated means that is fine. If minimum 50 percentage is not coated, then we need to again increase the percentage of pre-wetting water content. In addition to this coating test, we also can perform the maximum dry density test. So let us say I have chosen X percentage of the pre-wetting water, then I will perform the maximum dry density, then I will see the density, then I will keep increasing the water content and I will see. So I will get a curve like this, where this is the density and this is the pre-wetting water. So there is certain amount of water, we will get the density as the maximum. So we choose that water content as the pre-wetting water. So this pre-wetting water defines that this much amount of water is required to wet the existing gradation. So this is what the existing extra water. So in addition to that, we have some other extra water in the emulsion. So that water actually is required to make the bitumen suspended. That means in order to maintain the less viscosity of the bitumen. So now we have calculated the pre-wetting water content at maximum dry density. In addition to that, we also have the liquid content in the emulsion, initial emulsion content. So these two together is called as the total liquid content. Okay. So total liquid content, how do we fix the total liquid content? So in order to fix the total liquid content, what we have to do is, we have to prepare the Marshall specimen and we have to use the blows as 50, using this pre-wetting water content and also the initial emulsion content. So this IEC is fixed. That means we initially first we fix the initial emulsion content and we start increasing the water content. Let us say 1%. Then we prepare the Marshall specimen. Then those Marshall specimens we wait for 24 hours. Then we remove it from the molds. After removing from the molds, we will keep them in the oven for around 24 hours at 40 degrees. Again we take them out of the oven, then we keep them at room temperature for 24 hours. So once that is done, those specimens we will test for Marshall stability at room temperature. So we keep repeating this process. So now I have used, let us say, 1% of water content. I have fixed the emulsion content and I have calculated the stability. Now I increase the another water content. I will again keep the specimens for the conditioning. I will calculate the stability, and at some stage, see, this is the water content and this is the stability. So you will observe maximum stability corresponding to some liquid content. So that is what optimum total liquid content. So this is the water content at which the stability is maximum. That means at this water content, between the emulsion would be in the stable, and also the amount of pre-wetting water also sufficient. So once if we finalize the water content, now let us come. Initially we have calculated the initial residual bitumen content. Now we don't know that is that the bitumen content which will give the optimum performance. Now we have to calculate the optimum residual bitumen content. So what do we need to do? Now we need to change the residual bitumen content, because bitumen, what is the optimum residual bitumen content we wanted to calculate. So we need to vary that by changing the emulsion content. Previously we have kept the emulsion content as constant. Okay. So this pre-wetting water to be changed for maintaining the optimum total liquid content. So optimum total liquid content we have already defined, let us say from previous step. So we have to maintain this optimum total liquid content as constant, but we will be varying the residual bitumen content. Let us say at 1 bitumen content we will 1 RBC we will cast the Marshall specimens and we apply these 50 blows, and we will calculate the stability. That stability we define as dry stability. Same specimens, in the same manner we will calculate the soap stability. So how do we soak them? Let us say cold mixes, as we know, if we soak the specimen completely in the water, they will be stripped off, okay, because they have not been compacted at the higher temperatures. So that is the reason why when we are soaking, we have to soak half the depth for 24 hours. Again after another 24 hours, we will reverse the specimen and we will again soak. Once that is done, so we will dry the specimen and we will calculate the stability. So now we have the stability of wet and also stability of dry. So this is what called retained strength, retained tensile strength. So after calculating the retained tensile strength, then whatever that optimum residual bitumen content which gives the optimum properties, that optimum bitumen content will be chosen. So what are those criteria? So now we have all the stability values with all RBCs. So what is estimated with this optimum residual bitumen content? One is soaked stability, dry density, air voids and flow values. Just like volumetrics we have for the hot mix asphalt, where VMA, VFB and air voids unit weight, here we have to consider the soaked stability, dry density, air voids and flow value. So if we have insufficient stability or voids, or the, let us say, sometimes it might happen that the soaked stability must be satisfying, but sometimes air voids must not be satisfying. That means the level of compaction is not sufficient. So we need to change the level of compaction sometimes, and again we need to redesign. But finally what is the criteria is air void should be in the range of 8 to 14. So whatever the residual bitumen content I have changed and calculated the stability for dry and also soaked stability, all those specimens should have 8 to 14 percentage of air voids, but in the HMA it was 3 to 5%. And also once this is reached, that means when we design the Marshall mix design, When the air voids are 4%, we choose the corresponding bitumen content as the optimum bitumen content. Here for the air voids in the range of 8 to 14%, we can choose the optimum residual bitumen content. So here is the summary. Let us say, initially we calculate the initial residual bitumen content using this formula. Once the initial residual bitumen content is known, so this initial residual bitumen content divided by bitumen content will give, divided by the percentage of bitumen in the emulsion will give initial emulsion content. So once the emulsion content is known, so now you know the emulsion content, let us come to the water. So first we will start with the pre-wetting water. So whether the amount of water is sufficient to pre-wet the gradation. For that we perform the coating test and dry density test. If the 50% of coating is achieved and if the maximum dry density whatever corresponding to that water content, we choose as the optimum pre-wetting water content. So once the optimum pre-wetting water content is reached, so this is not the total water content. In addition to that, some extra water content is required. That is what called as optimum total liquid content. So in order to finalize that, we need to perform the Marshall stability. So pre-wetting water content at maximum stability plus water in the, so this total liquid content is nothing but the pre-wetting water content plus water content in the emulsion. And once this optimum total liquid content is finalized, how do we finalize? We calculate the density curve by changing the water content. So the content corresponding to the maximum dry density would be the optimum total liquid content. So once the optimum total liquid content is finalized, now we have to calculate the optimum residual bitumen content. So now we will keep the optimum total liquid content constant, then bitumen content we will try to vary. When I am saying that I am varying the bitumen content, that means that I am varying the emulsion because bitumen is present in the emulsion. So then optimum residual bitumen content is finalized based on these four. One is the Marshall stability. Here the stability, soaked stability plus dry stability, both criteria has to be satisfied, and also the air voids and the flow. Okay, so once all these things are satisfied, we finalize the optimum residual bitumen content. So let us solve few questions based on this theory of lecture 9. The number of gyrations in a superpure mix design is a function of. So if you remember, initially the 5 gyrations or 6 gyrations, 10 gyrations, these are the gyrations, let us say corresponding to N initial, N design, N maximum. So we have chosen this number of gyrations based on which criteria? Let us come to the options. So is option A design air voids. Did we ever choose the number of gyrations based on air voids? No. Now let us come to the temperature. Have we taken the location temperature? No. Have we taken the gradation? No. But we have selected the number of gyrations based upon the expected traffic level. If the traffic is less than 30 MSA, we have number of gyrations corresponding to N initial, N design and N maximum. And if the traffic is more than 30 MSA, we have another criteria. So the answer is B. So number of gyrations in the superpure mix design is based upon expected traffic level. Occurrence of plastic flow is in superpure mix design is controlled by. So whether my mix will have plastic flow or not, based on which criteria given below, we can actually define. So if you remember, N initial is we have 9.5 to let us say 11% of air voids. This is to check the compactability. N design is to check the 4% air voids. But if we come to the N maximum, this is to confirm that air void should not be less than 2%. Why are we checking the air void should not be less than 2%? If the air voids are less than 2%, which implies that most of the voids are filled with bitumen, then we do not have sufficient space, which implies that plastic flow in the future. So whenever we are checking for N maximum means, we are indirectly checking the plastic flow occurrence. So option C. For a polymer modified asphalt mix prepared using modified Marshall method, the maximum allowable flow value should be. If you remember in the today's class, so we have the flow range given for both modified and unmodified binders in the MRTH. But we have discussed that modified bitumens having higher elasticity, especially let us say polymer modified bitumens, even though if you suggest let us say 2 to 4 mm, we should not depend upon this. That means modified bitumen should not have more than 4 mm. That criteria should be waived off because there is a chance that modified bitumen mixtures can have higher flow, but still they can perform better because they have greater recovery. Even if they show the flow more than 4 mm, given the time they can actually recover. So this maximum allowable flow value should be waived off. And the fourth question is, this is a question we will solve. The optimum binder content of a recycled asphalt pavement wrap mixture containing 30% wrap is 5%. That means binder content in wrap is given as 5% and the wrap percentage is given as 30%. The binder content in the wrap is measured to be 7%. So let us, there is a wrap, 30% is of wrap in the total 100%. In the 30%, 7% is the bitumen in the wrap. And to this wrap, I have already mixed the new virgin aggregates and new binder. I have prepared the mixture and the optimum bitumen content of that new mix is 5%. So now the question is, calculate the percentage of wrap binder in the final wrap mixture. So final wrap mixture has 5. Okay, the OBC is 5% means final wrap mixture has 5% as the OBC. So in this 5%, how much is that 7% of wrap binder? So 7% of, so this is the wrap percentage. In this 30% of wrap, 7% is the binder. So this total binder, whatever is numerator, in out of 5, in terms of percentage would be. So if we calculate this, we will get the value as 42%. And here if you see another question, for the given data, calculate the GMB of a 60% wrap mixture. So we have to calculate the GMB of wrap and the wrap percentage is given as 60%. So in the given 100%, 60% is wrap. That means remaining 40% would be virgin aggregates. Okay. And also please observe here, wrap percentage is more than 25%. If the wrap percentage is more than 25%, how do we calculate the GSB? So first we have to calculate the GSC value. Using this GSC value, we have to calculate the GSB value. So how to calculate the GSC value? To calculate the GSC value, we need the GMM and also percentage of binder and also the specific gravity of the binder. So you can see the formula here, let us say. So we have to calculate the GSB. To calculate the GSB, we need GSC, binder absorption and also specific gravity of the binder. But we know effective specific gravity as GSC from here. Percentage of binder in wrap. They have given 7%. What is the percentage of binder in wrap? 4.5%. So you can see here, percentage of binder is 4.5. Okay, this is 4.5. and the GMM. GMM is given as 2.545. GMM is given as 2.548. Absorption is given, GB is given, GSP is given. So all the details required here are given. So we can calculate GSC. So once the GSC is calculated, if we substitute here, we will get the GSB. So that is not the final answer. The GSB which I am calculating here is the GSC of RAP aggregate. But in the question, they have asked the GSP of mixture. How do we get the GSP of mixture? Let us say total is 100%. In that 60% is the RAP divided by GSB of RAP we have to calculate, plus remaining 40% is the virgin aggregates divided by GSP of virgin aggregates. So this GSB of RAP you are calculating here. Okay, GSP of virgin aggregates already they have given. So if we substitute these two values, finally you will get the GSP of mix. So this much will be the GSC, GSB and also GSP of mix. Let us say if the RAP percentage is not 60%. So in the question, if the RAP percentage is 10% or 20% only, then how do we calculate the GSP? First we will calculate the GSC based on the formula. Whatever the GSC we have calculated, we will take that as the GSB. Once the GSB is known, GSB of RAP is known, again the process is same. 100 by 60% of which is RAP by GSB of RAP plus 40 is virgin aggregates divided by GSB of virgin aggregates which is given here. So only difference would be we consider GSC as the GSB if the RAP percentage is less than 20%. Let us see another question. For the following data, calculate the maximum percentage of RAP that can be used. So what are the given? Optimum binder content of the mix 5%. Amount of binder in the RAP is 5%. Viscosity of RAP 10,000. Target viscosity 4,000. Viscosity of the virgin binder is 3,000. If you remember our blending chart, so we need blending chart to calculate. So in the blending chart, viscosity is here and that new binder blend is here. So what is given in the question? Viscosity of RAP binder at 60 degrees is given as 10,000 poise. So as I have mentioned previously, here RAP 100% is represented here. So the RAP viscosity corresponding to that they have mentioned as 10,000. Okay, one of the data given. Another is target viscosity of the final blend is 4,000 pascals poise. So somewhere we don't know how much percent it is. Somewhere the target viscosity is 4,000. And also another data given is viscosity of virgin binder is 3,000. So 3,000 would be here somewhere. So here what we have to observe is, let us say there is some RAP aggregate. Upon this RAP aggregate there is some binder. So this has some viscosity and to this mixture RAP having some aggregate binder around that, to that we are going to add some new binder. So this will have another viscosity, let us say eta 2. So together when these two are mixed, we will get the final RAP mix. This final RAP mix, how do we get? When we add the existing binder on the surface of the RAP aggregate plus some new binder, we will get the RAP mix, and this binder whatever is present will have some viscosity which is eta 3. So in the question they have given that the RAP binder has 10,000 viscosity and this new binder has around 3000 viscosity, and they are expecting that by mixing 10,000 viscosity and 3000 viscosity they are expecting 4000 viscosity which is the target viscosity. So let us combine these three. So now the question is, if I wanted to get 4000 viscosity binder but I am going to add 10,000 viscosity wrap binder, 3000 viscosity new binder, then how much wrap percentage I have to add? Okay. On this x-axis, wrap percentage starts from 0% here to 100% here. So same axis we will use for virgin aggregates also. 0% here, 100% here. Okay. So we have to calculate the wrap percentage. That means this one. This percentage we have to calculate. So let me draw here the triangles and let us calculate here. So now we have a triangle like this, which is the y-axis is a log axis. Okay, don't forget that. So this is log of 10,000. Somewhere it is log of 4,000 and somewhere it is log of 3,000. And we do not know this. Let me assume it as x. And we know that this entire bar is 100. Okay. So from the interpolation, what can be written? Log of 10,000 minus log of 4,000 divided by log of 4,000 minus log of 3,000. This will be on left hand side, and this you can equate as, that means I am saying that this log of 10,000 minus 4,000. So you will get this part divided by log of 4,000 minus 3,000. Then you will get this small part. Okay. So this part by this part I am doing. We know this angle will be same. That's why. On the right hand side, what we will be doing? 100 divided by 100 minus x. So 100 this entire, and if I remove this part will come. So this total bigger part by smaller part I am doing. This is just an interpolation you can do by yourself. So when you solve this, you will get some x percentage. So this x percentage will be around 77 point some percentage. But here x is not the wrap. You have to understand that. On this total 100, if you remove the x, whatever this is there, this is what wrap. So 100 minus that whatever 77 point something you will get, 23.9% is what your wrap percentage. Okay. So in this kind of problem, the main thing is in the blending chart, out of that 4, they will miss one data. So you need to calculate that data based on the remaining 3. It is just based upon the interpolation. The approximate temperature range of providing cold mix asphalt is. This we already know. We have seen an image where cold mixes are prepared in the range of 0 to 30 degrees Celsius. Pre-wetting water content in the cold mix asphalt can be determined using. So initially when we add the pre-wetting water to the gradation, how do we confirm that there are sufficient pre-wetting water is there? We have two tests. One is coating test, minimum 50% of the gradation should be coated, and another is the maximum density. How do we calculate the maximum density? Using the Proctor density test. Okay, so option C is the correct. During the determination of total liquid content in cold mix asphalt, Marshall samples are prepared at. Okay. If you remember the total optimum total liquid content, which is nothing but pre-wetting liquid content plus the emulsion liquid content. Okay. So what we have done, we have prepared the master specimens and we compacted them to the 50 blows, and then these 50 blows are the criteria used to determine the optimum total liquid content. And the last question is, if VG40 is the standard binder used in the construction of national highway, what should be the grade of the binder to be adopted if the 10% of RAP is used? So if you could have remembered, if the RAP percentage is less than 15%, then what kind of grade we have to choose is, we have to choose the grade, let us say this RAP has VG40 they are saying. So to this RAP, now I have to add some new binder. So which grade of binder I should add? It depends upon the amount of RAP percentage. If the RAP percentage is less than 15%, you can use same VG40. So here the question is, if the 10% RAP is used, 10% is nothing but the less than 15%. So they can go for VG40 directly. So VG40 is the direct answer. Okay. Are there any doubts to discuss further? You can turn on your microphones and ask. Are there any doubts in the chart? Okay. If there are no other doubts, please repeat the concept GFP of final mix of RAP. Okay. So if you could see GSP, so initially when we have the RAP is nothing but the aggregate coated with binder. So those aggregates we have to calculate the specific gravity. That is called as GSP of RAP. And also to this we might be adding some new virgin aggregate. Okay. This new virgin aggregate will have some specific gravity. That is called as GSP of virgin aggregates. Okay. So now I am mixing the RAP with the new aggregates. Then I am mixing that is called final RAP mix. So final RAP mix will have different bulk specific gravity. So in order to calculate that GSP of, that is called as GSP of RAP mix. So how do we calculate? Let us say total mix is 100%. So in this 100%, 60% is RAP used. So then corresponding bulk specific gravity of RAP is this one, GSP of RAP plus. So if 60% is RAP, the remaining 40 will be virgin aggregates. And what is the specific gravity of that? GSP of virgin aggregate. This concept is exactly like when we do the GSP of virgin aggregates, how do we used to do? If the 60% is the coarse aggregates and 40% is the fine aggregates, and if the specific gravity of coarse aggregate is GSP of Ca, if the specific gravity of fine aggregates is GSP of fine Fa, then how do we used to do? Total is 100 divided by 60 divided by GSP of coarse aggregate plus 40 divided by GSP of fine aggregates. Because in the total virgin aggregate, 60% of coarse aggregates are there, 40% of fine aggregates are there. Then we take the corresponding specific gravities and we calculate the final specific gravity or final bulk specific gravity. In the same way, in order to calculate the final bulk specific gravity of RAP mix, if we know the specific gravity of RAP aggregates, if we know the specific gravity of virgin aggregates, and if we know their proportions, we can calculate using this formula. Okay, anything else? If there is nothing, yes, RAP binder percentage. RAP binder percentage, yes, what was the question? So initially we have to calculate the wrap binder percentage. How to calculate the wrap binder percentage? Okay. So let us say 25% is the wrap. So we have to calculate in this, when I say 25% wrap, that means aggregate is there, around that aggregate some bitumen is there. So now we have to calculate how much bitumen is there. So for this, first we have to perform the extraction and recovery process. So let us say I will take 1 kg of wrap. When I take wrap, it has aggregates and the coated bitumen also. I will take this 1 kg of wrap, then I will mix with the solvent. Let us say trichloroethylene is the solvent. Why am I mixing with the solvent? I wanted to dissolve the surface of the aggregates. So I will dissolve that, then I will separate that bitumen. Then that bitumen, now it is not just the bitumen. It also has the solvent which is trichloroethylene. So I will take that and I will recover. That means out of the solvent plus bitumen, I somehow will remove that solvent. Let us say trichloroethylene. So whatever remained will be bitumen. So if we get out of this 1 kg of wrap aggregate, finally you will get some amount of bitumen, right? So that binder will be expressed as a percentage of the total initial wrap weight, that we can call it as a binder percentage in the wrap aggregate. We can also use ignition and other methods, but most predominantly used was the extraction and recovery method.
Ma'am, which formula is used to find the rate binder percentage calculate?
We do not have any formula. Usually we have to do extraction and recovery process. So from that process, whatever the final binder you are getting, let us say you got 50 grams out of 100 grams of wrap, then 50 by 100 into 100. So that is how you calculate the percentage.
Ma'am, you have a question in our assignments. So how we solve this question?
So we have solved similar kind of question, if you could have seen.
Okay.
See, this question number 6, I suppose, is similar kind of question. So using the blending charts, if you see here, so if you see in the blending charts, in this current set, 10,000 is what given in the problem, my problem. But in your problem, the drab binder viscosity is given as 14,000, isn't it?
Yes,
Yeah.
yes ma'am.
And the virgin binder viscosity in my problem is around 3,000, in your problem also same. And the target viscosity in my problem is 4,000 and in your problem also 4,000, and remaining all are same. So this is exactly kind of similar problem, and you can also find this similar problem in the video also. The values were different. Okay.
Okay.
Okay then, thank you for joining. I'm closing the meet.